Hey guys, welcome to part 2 of work, energy and power. Just like we've discussed energy in part 1, today we are going to discuss the principle of conservation of mechanical energy. So in this video we are going to look at isolated systems, the definition of mechanical energy. We will then proceed to the conservation of mechanical energy, and we'll later on solve a few problems. Now, firstly, we are going to look at what an isolated system is. According to this definition, it says that a system on which no external forces act. Such external forces will be referring to friction. If not friction, then other ones like applied force, right? So friction and applied force, those are the two most common external forces. So it means that in an isolated system, the only forces that you will find is only internal forces, right? And what are those internal forces? This is the weight, and sometimes you will find the normal force, which results from contact with a surface, right? So two forces that are not supposed to be present in order for us to consider a system as isolated. It's the frictional force and the applied force, or any other force which can be introduced externally. So it simply means that if I'm given a slope, and then I'm told that an object is sliding down slope at a certain velocity, provided that this object there's no applied force, and also that the slope itself is frictionless or is rather smooth, then we can say that this whole system is isolated, meaning external forces do not play a role in the system. They do not interfere with the system. The only force that we have, or the only forces, is the weight, which causes the block to slide down slope, and the normal force, which is perpendicular to the slope, that results from contact between the slope and the object itself. So in order for us to say a system is isolated, applied force mustn't be present, as well as frictional force. In our past video, we discussed mechanical energy. We said mechanical energy is the sum of the gravitational potential energy and the kinetic energy of an object. We said mechanical energy, which is EM, is equals to EK plus EP, right? Yes, and then EK, remember this is the kinetic energy, which is half mv squared, plus the gravitational potential energy, which is mgh. Remember, gravitational potential energy is the energy that an object possesses due to its height or elevation from the Earth's surface. And then we said mechanical energy is the energy due to motion of an object, right? And then we said at any given point, an object will always have a mechanical energy, which is the sum of these two. Say maybe we have this curved slope going like that. We have a certain height, which is height 1, and then we have a certain height, which is height 2. At that point right there, we have the mechanical energy, provided that, say, an object is moving at a particular velocity, then the mechanical energy at that point is simply the sum, just like we've said, right? Plus mg, and what's the height? The height is height 1, since we're taking that as the reference point. And even at height 2, we still have mechanical energy. Remember, it's the sum of the two, half mv squared plus mg, but now it's h2. And then the object will have a certain velocity, because as it's sliding down slope, it's gaining more energy, right? More kinetic energy. So for today, we are going to introduce the principle of conservation of mechanical energy. It says that the total mechanical energy, we spoke about mechanical energy being these two, the sum of gravitational potential energy and kinetic energy. In an isolated system, we just discussed an isolated system. What did we say an isolated system was? We said an isolated system must have no external forces. And what are those external forces? It's applied force and frictional force, right? Yes. The total mechanical energy in an isolated system remains constant or is conserved. So it means no energy is lost here. We are not losing energy. No energy lost, right? That's why they say it remains constant. we are simply converting energy. So we are taking energy from one form to another, right? And we are converting from what to what? We are converting either from potential energy, gravitational potential energy, to kinetic energy, or the other way around, but it exists between these two. Hence, the law itself, the principle itself says that the mechanical energy at a certain point, which is the initial point, is equal to the mechanical energy at a certain point, which is the final point. But what's the mechanical energy? It's the sum of the kinetic energy and the gravitational potential energy. Remember, this is point 1, which is the initial point. And then now at the final point, the mechanical energy at the final point is the kinetic energy at that final point plus the gravitational potential energy at the point. So what's this? This is now half mv. Now it's the initial velocity. It's the velocity at the initial point plus mg at that point, which is equals to, now it's half mv, but this is what? This is the final velocity. It's the velocity at certain point 2 plus the gravitational potential energy, which is mgh2, right? So this is the principle itself. It says that the mechanical energy at a certain point 1 is equals to the mechanical energy at a certain point 2. So let us quickly explore that further. So let us look at the given problem right here. A 2 kg box is released from rest. Yes, it's released from rest. That's very much important. It means the initial velocity at point P is 0. And then point P is 5 meters above the ground. It slides down a smooth frictionless surface. Now that's very much important. Smooth frictionless. Firstly, if we look at that block, there's no applied force, right? We have no force applied. And on top of that, they just told us it's smooth frictionless, meaning there's no friction. So what does this tell us? It tells us that the slope PQ, while the block is sliding down the slope PQ, the system will just be an isolated one, meaning there's no external force that will be acting along that path. And then the first question says, state the principle of conservation of mechanical energy. We just said it. The total mechanical energy of an isolated system remains constant, or the total or net mechanical energy of an isolated system is conserved, right? Now I want us to look at number 2. It says use the principle of conservation of mechanical energy. They are being specific now which principle you should use, right? And we said in order for you to use the principle of conservation of mechanical energy, the system must be isolated, and then while it's an isolated system, no external forces acting, force applied or frictional force. And indeed, between the points P and Q, we can apply the principle because there's no external force acting. So let us proceed. We are going to have, so the mechanical energy at point P must be equal to the mechanical energy at point Q. So this is 5.2. And remember that the mechanical energy is the sum of kinetic energy at point P and the gravitational potential energy at point P, which must be equals to the sum of the kinetic energy at Q with the gravitational potential energy at point Q. Remember, this is half mv, but now what's that? It's the velocity at P squared plus this is mg plus the height at P, which is equals to half mv, the velocity at Q squared, plus mg, the height Q. So now if you look at this, we have that the block is released, right? It was released from rest. So this is just half into the block's mass is 2 into the velocity is 0 because it's released from rest. Now we have the mass again, which is 2 times the gravitational acceleration, which is 9.8. What's the height? The height at P is given as 5 meters there. So we have 5, which is equals to half into 2 into, what's the velocity at Q? It's exactly what we are looking for. So use energy principles to calculate the speed of the block as it reaches point Q. So we are looking for the velocity of Q, at Q, plus the mass now again is 2 kg times the gravitational acceleration, which is 9.8. Now what's the height at Q with reference to the surface or the ground? It's just 0, right? Yes. So we can see that this term will go to 0 and even that one will go to 0. Multiplication by 0 will simply give you a 0. So then we have that this is 98, which is equals to, this will cancel that, so we have VQ all squared, and lastly we need the square root, so VQ will simply be the square root of 98. So VQ is equals to 9,90 meters per second, and then it's moving to the right. Remember, velocity is a vector, it has both magnitude and direction. And then if we try to look at the other questions, it says that the box passes point Q and moves 10 meters on a rough horizontal surface. Now here's the problem, it's now a rough horizontal surface between the points Q and R, right? Striking the barrier at I at a speed of 4 meters per second. Use energy principles to calculate the magnitude of the average frictional force as soon as it's a rough surface, no longer isolated. It's not an isolated system anymore, right? So it means we cannot use the principle of conservation of mechanical energy, but we can use other means which we will explore as we keep on with the course. Let us look at another example. Let's look at this one. A slide PQR at an amusement park consists of a curved frictionless surface PQ. So it's this section right here, PQ, which is frictionless. Then that makes it a what? Since there's no applied force again, it makes it an isolated system right there. And a section QR which is rough, so they are being specific that QR is rough. So this part from Q to R, it's not an isolated system because there's an external force acting, which is frictional force due to the roughness of the surface. Okay, the surface QR is inclined, is rough and straight and inclined at 30 degrees to the horizontal. The starting point P is 3 meters above point Q, and the straight section QR is 5 meters long. A learner with the mass of 50 kg, so we are given the mass there, so the mass is equals to 50 kg, starting from rest at point P, so it means the initial velocity is 0 there at P, Vp is equals to 0, and slides down a section PQ and continues down the straight section QR. State the law of conservation of mechanical energy, which I spoke about it. The total mechanical energy of an isolated system is conserved or remains constant, right? Calculate the speed of the learner at point Q. So they are looking for the velocity at that point, which is Q. Now here's where I'd like us to start. Remember that the gravitational potential energy is always calculated with respect to the ground as reference point. So we will start by calculating this height right here so that we know the exact height of P with respect to the surface. If you look at this, it gives us a right angle triangle in which this is point R, in which this is point Q, and we just have this height here. What's that height? That's HQ. That's the height of point Q. So what's this? It's 30 degrees. We are given the hypotenuse, which is 5 meters. If you look at HQ, HQ is actually the opposite side. So we are going to use the sine of that angle. So sine 30 is equals to the opposite, which is HQ, divided by the hypotenuse, which is 5. Multiply both sides by 5. We get that HQ is then equals to 5 multiplied by sine 30, which is then equals to 2,5 meters, right? So we have the height there, height Q, which is 2,5 meters. So we'll measure this to be 2,5 meters from the surface. So this simply means that the height at P is 3 plus 2,5 because it's this small portion plus that we are measuring with respect to the ground, remember, which gives us 5,5 meters. So we can proceed to use the principle of conservation of mechanical energy because we know that PQ is a smooth, frictionless surface, meaning the system will be isolated. So the mechanical energy at point P is equals to the mechanical energy at point Q. But what does that mean? Mechanical energy is the sum of kinetic energy at P with the gravitational potential energy at P to give us the sum of kinetic energy at Q with the gravitational potential energy at Q. But what's this? it's half mv, it's the velocity at p squared, plus mg, it's the height at p, and then this is half mv, it's the velocity at q squared, plus mg, it's the height at q now. But then if you look at this, remember that the block was released from rest at p, so the velocity there is 0, meaning this term will simply go to 0. So we are left with mg, height at p, which is equals to half mvq squared plus mg, height at q, right? What we're looking for, we're looking for the speed of the learner at point q, so we are looking at vq right here. Direct substitution, we have the mass as 50 times 9,8. What's the height at p? It was calculated to be 5,5 meters with respect to the ground, which is equals to half of the mass as 50, and then we don't know the velocity at q, plus 50, 9,8. What's the height at q? The height at q was calculated to be 2,5, right? So this gives us 2695, which is equals to half times 50. This is 25 vq squared plus 1225. So now we transpose the 1225, so it's 2695 minus 1225, which is equals to 25 vq squared. The rest is just algebra, right? And this will give us 1470, which is equals to 25 vq squared. Divide both sides by 25 to 8,8, which is equals to vq squared. So what's vq? Vq is just the square root of 58,8, 7,67 meters per second, 67 meters per second. So let us look at the last example. So it's considered a 20 kg block sliding on the frictionless slope ABC. So the whole slope from A to B to C is simply frictionless, and as you can see, there's no applied force there, making the whole slope an isolated system, right? The block and slope system, an isolated one. The block is initially at rest at point A, so we're given that this is velocity there is simply equals to 0. Calculate the following: the velocity of the block at point B. So now we can do this in sections. We can see that the block is sliding from point A to point B, so we can use the mechanical energy between those 2 points, because we know that this is an isolated system. The mechanical energy at point A is equal to the mechanical energy at point B, right? Remember, the total mechanical energy of an isolated system remains constant. So we can apply that knowing exactly that it's an isolated system. But remember, this is the sum of kinetic energy at A and the gravitational potential energy at A must be equals to the sum of kinetic energy at B plus the gravitational potential energy at B. What's this? It's half mv b squared plus mg, and then it's the height at A, which is equals to half mv b squared plus mg, height at B, right? But now we're told that the object is initially at rest, meaning the initial velocity at A is 0. So that term will simply go to 0. And what do we have? Have the mass of the object, which is 20 times 9,8. What's the height? The height is 4 meters, which is equals to half. Remember, the mass of the block is 20 into the velocity at B is what we are looking for. So it's the velocity of B all squared multiplied by, this is 20 times 9,8. What's the height at B? It's 1,9. So this gives us a total of 784, which is equals to half times 20, simply 10, velocity of B squared plus 372, right? Transpose that term, we have 784 minus 372, which is equals to 10 VB all squared. And this gives us 411,6, which is equals to 10 VB squared. Therefore, the velocity at B is just going to be the square root of 411,6 divided by 10. So that has to be 6,42. So VB is equals to 6,42 meters per second in that direction, right?